I would like to start the session and welcome Professor Jutta Kunz to give her talk on the ringdown of rotating black holes.
Yeah,
Kunz.
thank you very much for this very nice introduction. And thank you so much also for the invitation to this really nice conference. It's an honor for me and a pleasure, of course, to participate in this meeting. I myself think I only had once in my life the opportunity to meet Professor Mitra when we had this meeting 2013 in Delhi, organized by the nuclear physics group and my friends Usha and Jaya Gulshrest. So now with this session, I think we switch a bit from the nuclear physics to the gravity, and we did have already a little bit in the first lecture of this conference on the ringing of black holes, but now I'll talk a bit more about it, and in particular I'll go to rotating black holes. And no, it doesn't work. It did work all the time, and now it works. I would like to give you the outline after an introduction, and it'll be a little longer because it's now switching topics to gravity. Then I'll talk about a specific type of black hole and about the ringdown and testing Einstein's general relativity, and then I'll end. Now, here you see the beautiful Einstein equations, and on the left-hand side you have the gravitational part, the curvature, which is what or how Einstein describes gravity, and on the right-hand side you have the energy momentum tensor. So you have a rather complicated looking set of equations already for general relativity. It's nonlinear partial differential equations that need to be solved. But Karl Schwarzschild, this German astronomer, he immediately realized that if he gives sufficient symmetry to the problem, he can find a solution, and he was interested in describing the solar system. So he assumed that the space-time is static and that it's spherically symmetric, which is a wonderful approximation for our solar system outside the sun. But then when one looks at the whole solution and also allows for the inside, so does not look at the matter of the sun, then one arrives at this surprise, namely one finds the first black hole of general relativity, the Schwarzschild black hole, the famous static spherically symmetric black hole. And it's really very simple. It's given by a single quantity, basically the mass. The mass determines the event horizon, and inside it has a singularity. Now, when we look at our universe, almost everything is rotating, right? The Earth is rotating, the sun is rotating, and the stars. So one is expecting, if there would be black holes in the universe, they would be rotating. And so we have to generalize the Schwarzschild black hole to a rotating black hole. And this was done by Roy Kerr almost 50 years after the Schwarzschild solution was found. And it's been believed and beautifully expressed by Chandrasekhar that this myriad of black holes that is residing in the universe is probably, at least to a high degree, described by Kerr black holes. So these Kerr black holes, they are now stationary, and they are only axisymmetric. They are rotating, so they have some deformation. And they have this funny, surprising property called ergospheres. So within this region here in the figure, you see it as green. Within this region, everything has to rotate along with the black hole. And inside the singularity is now no longer point-like, but ring-like. But let's forget about the inside. We are interested in the outside and our universe in the observable part. And still, these Kerr black holes, they are very, very simple. They have an enormously high degree of symmetry, and they are characterized by just two numbers, by the mass and the spin. And so Wheeler said black holes have no hair, because yeah, that's all you need to know. The mass and the spin, and then you have the whole space-time. And they have even some hidden symmetry, which is very, very helpful in general relativity when studying black holes and their properties. So we have what is called the Kerr paradigm, saying that most probably all the black holes in the universe are very well described by the Kerr black hole solution. But maybe there are some deviations. And this means we would like to test gravity. We would like to test general relativity. And yeah, there's various reasons to think that general relativity is going to be superseded by some other more deeper going theory of gravity, including quantum mechanics somehow. And so one is looking for tests, and also, of course, from the cosmology side, we know there's all this dark part of the universe, the dark matter, the dark energy. So maybe we can describe the whole thing in a more comprehensive way. And so we are looking for testing the Kerr paradigm, testing general relativity. And very nice tests are now available to us. Namely, we can watch the gravitational waves that are emitted when these objects, black holes or neutron stars or mixed systems, when they inspiral and then merge and then ring down. So we have these three phases of such a merger event. And in this talk, I will focus on the last, namely the ring down, and see what type of deviations might we expect by looking at theories beyond general relativity. So this will be mainly what I'll be talking about, but there's of course other tests, and one also very nice is done by looking at the shadow. The Event Horizon Telescope collaboration has obtained these beautiful images of the black holes in M87 and in our Milky Way. And yeah, for both, for gravitation wave tests and for these tests of the shadow, general relativity does perfectly so far. However, if we have future observations, more accurate observations, possibly one might find some deviations and then get some hints towards how some deeper theory of gravity might look like. So when we're going to such a theory, of course, whatever theory of gravity one is thinking of, one does have to respect what is known, namely solar system tests. Everything that is known in the solar system must be satisfied by any viable alternative theory of gravity. But in the strong gravity sector, where we have black holes, where we have neutron stars, and possibly some exotic compact objects, and the next talk will address some exotic compact objects like boson stars. So there's still some freedom, and so there we would like to find constraints. So now let me focus on one specific theory which we have studied a lot and other people have studied a lot. And this is called Einstein scalar Gauss-Bonnet type of theories. Here you see the action, and this first piece here, this is just the Einstein-Hilbert action. And then this last piece, this is called the Gauss-Bonnet term. It's a term that is quadratic in curvature. And here you see how it looks like. And this is the first term that actually arises when you go to higher dimensions. So the first Lovelock term. And Naresh Dadic is very fond of these, will be the last speaker of our session. And in 4 dimensions, this term by itself does not contribute. However, if it's coupled to a scalar field, and here you see some coupling function to some scalar field phi, then it does contribute, and we obtain this set of theories, the Einstein scalar Gauss-Bonnet theories. And they are quite nice from various points of view. For instance, such types of theories arise when you look at the low energy effective action as you obtain it from string theory, or when you do some effective field theory expansion in the derivatives of the metric. So these terms always arise here. Of course, we use special coefficients, but the Gauss-Bonnet term arises in string theory, but then coupled to a special scalar field, the so-called dilaton. So one has some theoretical motivations to study quadratic curvature corrections to general relativity. And this way, with the Gauss-Bonnet term, this is particularly nice because one obtains a set of second-order differential equations, and this is what one is used to from Einstein's theory. So let's now look at the black holes that arise in this theory. And the first papers you see here, 95, 96, are quite old. And the motivation at the time was basically string theory. And so the coupling function was taken to be a dilatonic coupling function, which means you have some exponential coupling to the scalar. And alpha is taken to be a free coupling constant. And then for this theory, the static black holes were obtained. And here you see in this figure, the horizon radius versus the mass. And it's scaled by the coupling constant. And of course, for Schwarzschild, you just obtain a straight line. But when you now look at the black holes of Einstein dilaton Gauss-Bonnet theory, then there's a dilaton. So these black holes have hair, they have a scalar field, and this scalar field gets more important the bigger this coupling constant is. And for very small coupling constants, in the limit coupling constant to 0, you just go to Schwarzschild. And here you see up here towards this corner, you go to Schwarzschild. But then you see all of a sudden here, funny, the solutions stop. You don't go all the way to 0, but there's a minimal mass or a maximal value of the coupling constant for a given mass. So one has a critical solution, and in this type of theory, there's always some radicand that vanishes when one looks at expansions, and so this is right where the solutions stop, and we call them critical solutions, where you cannot follow to smaller masses anymore or larger coupling constants. Now, of course, we want rotation, right? So we have to rotate the black holes, and here we have the horizon area versus the angular momentum, both scaled in some way with the mass. And the static solutions we just looked at are residing here on the axis, and this dot corresponds to the critical solution. Up here, the black curve corresponds to the Kerr black holes, and whatever is shaded, you see, these are all the possible black holes that you have in this theory. So you have a whole domain of existence for such black holes, and the horizon size can be quite a bit smaller. And also very interesting for Kerr black holes, you have a maximum of the angular momentum, which is 1 when you scale it by the mass squared. But here, no. You can go a little beyond. This is the same plot, let's say now for the angular momentum versus the coupling constant, just to kind of point out again that you cannot go to too big coupling constants. Then there's just no more solutions in this type of theory. When you look at the shadow, unfortunately, you don't see much. It's not expected to be observable that you have such a small difference also with the next, I would say, generation of instruments, but there might be a possibility of making observations by going to gravitational waves. So there may be differences as compared to the Kerr black holes, because one has the scalar field present. A scalar field also allows for radiation that is lower than quadrupole, right? We can have dipole radiation, for instance. And so the coupling of the scalar with the gravitational field of the background solution is also producing some coupling in the equations, and so one expects some real effects if the coupling constant isn't too small. Of course, going to 0, we don't see anything because you go back to Kerr. So now let's look at the in-spiral phase and not the in-spiral phase, the ring-down phase. So let's first look just at this last piece after the merger, how this highly excited black hole rings down to its final state. And how do you do this? Now, you do some perturbation theory, you perturb around this hairy black hole. So you have perturbations of the metric and of the scalar field, and you can classify them into even parity and odd parity perturbations. And when you look at static spherically symmetric black holes, this is quite doable. You obtain some master equation, some Schrödinger-like equation for the eigenvalue, and the eigenvalue, because you have damped oscillations in the ring down, has a real part and an imaginary part. The real part corresponds to the frequency and the imaginary part to the decay time. So this is what one finds for the static black holes. And here you see the real part scaled with respect to Schwarzschild, and the imaginary part scaled with respect to Schwarzschild. And we start here at 1, because it's scaled with respect to Schwarzschild, and then we increase the coupling constant, and you see for large coupling constants, a lot of things are happening. So one obtains really deviations in the frequency and in the imaginary part. These are the axial modes, quadrupole axial modes. These are the polar axial modes. You see the scalar and the gravitational-led modes that kind of go to different directions here. But we really want to look now at the rotating modes, and I don't have too much time left. So let's now focus on the rotating modes. For Kerr, this has been done. And there's this very famous Tucholsky equation. And because of the very high symmetry of the Kerr black hole, one still gets some decoupling of the radial coordinate and the polar coordinate. For some general black hole, rotating black hole of whatever generalized gravity theory, this isn't happening. These black holes are too complicated. They don't have this high underlying symmetry. So in that case, one simply has to use, let's say, brute force. One has to discretize and use some spectral method or other method to solve a complicated coupled set of equations for these modes to obtain the eigenvalues. And that's the quasi-normal modes. So we have, together with our colleagues in Madrid, José Vázquez Salcedo and Fichsenko and Francisco Navarro Lerida, and also Luis Manuel González Romero. With them, we have developed some methods, some spectral decomposition using Chebyshev polynomials, Legendre functions, and we have tested it on the Kerr quasi-normal modes. This is a piece of the Kerr spectrum where you have the different L going in this direction and the overtones going in this direction, and we can get perfect agreement up to a number of digits. And so we were confident of applying this procedure to our first set of black holes, rotating black holes of some alternative gravity theory. And here you see small angular momentum still. So there we could also compare with perturbative calculations for perturbation and angular momentum, and we also agreed. And here you see on the left-hand side the frequency, on the right-hand side the imaginary part, and the most important modes are those that live the longest. So it's those, that are high up here. And you see for a general relativity, we have the quadrupole modes, and we have degeneracy of axial and polar modes, isospectrality. And then there's the splitting arising. So isospectrality is broken. And very interesting, as we go to very large coupling constants, then we see also the order of the modes. What is the most important mode? This is changing. And I must say, it came as a real surprise to us that, as you can see here, it's the scalar-led mode that is coming up and becomes the most important, the leading mode in this case. And we have done this for higher angular momenta.
Professor Kunz, you have 5 minutes.
5 minutes. Oh, I thought I have to be faster. Thank you. So we have studied this for a variety of modes, seeing how important it is to take all these modes into account and making some predictions. And we were hoping we would be able then to, with future observations, future gravitational wave observatories, be able to make some distinctions between the different modes there, and then be able to put some limits on this type of theory from gravitational waves. But actually, it turned out, basically at the same time when we were doing our calculations, colleagues in Potsdam did calculations of the full thing in some approximation, but they did also the in-spiral. And from this in-spiral, you obtain already now the best current bound on the coupling constant, so on this theory. Namely, here you see the Ringdown starting at some point with the same kind of starting conditions, initial conditions, and then the system is evolved with in general relativity in red, then light blue, some intermediate value of the Gauss-Bonnet coupling constant, and dark blue, some high value of the Gauss-Bonnet coupling constant. Yeah, it's normalized differently from what you saw before. But then, I mean, the main effect you can see here down in this diagram, you see the red curve ends here at 0. But as the Gauss-Bonnet coupling is increased, the merger, this Ringdown, the end spiral, it's basically the end spiral phase, this happens faster. So this end spiral phase then, this has additional radiation. It does not only have the quadrupole radiation, but we have a scalar, so there's also dipole radiation, and it's basically an effect of this dipole radiation that we see here, as these colleagues say. So there's the best bound currently on this type of theory from gravitational waves, but from the in-spiral phase. Now let me come to the conclusions. We have seen that the Kerr black holes after relativity have a very high degree of symmetry, and so they are very well to handle because of that symmetry. And basically everything has been done, and lots of things you can do analytically for them. But this whole merger process has been done by numerical relativity because the merger itself is too complicated to handle in whatever approximations. Now, when you go to theories beyond general relativity, and we would like to see some deviations somewhere, hopefully, giving us some direction where to look for. And then black holes can be much more complicated. They can possess hair. And this is now what many people in the community are doing, looking at theories that go beyond Einstein and try to look for observational signatures that might be possibly detected in the future. Thank you.
Okay, thank you very much, Professor Kunz, for that very clear signal, of beyond Einstein gravity in the ring down of black holes. We have time for a question or so. We are one, perhaps maybe two questions if they're brief. I see, just a second, Alok, Professor Alok Mishra, I can see your hand. Please.
Yeah, sorry, I just had a quick question. This is something which has always puzzled me. I mean, I don't work in this area, but I mean, when we're after all talking about a black hole merger, so what baffles me is how come first order black hole perturbation theory would suffice? I mean, I also remember coming across some Fitzgerald Leonard's paper a couple of years ago where they go up to second order. But I mean, I feel that this should be entirely non-perturbative in gravity. I mean, this should be not addressable within the confines of linear perturbation theory. Maybe I'm wrong. I'm missing something big.
Yeah, I mean, in this area here, this is where one is using basically the full numerical relativity, no perturbation theory, just solving the full set of equations, because whatever approximations you use don't suffice. You have to use the full thing. So, but these numerical relativity calculations are very long calculations. And so one is still trying, because one cannot do them for all kinds of theories. One is still trying to obtain information. And here in the Ringdown, yeah, one has a chance to obtain deviations, because yeah, it's at some point, and it's not quite clear when, this being under debate, where you should start fitting the quasi-normal modes. You might get then information just and bounce on the theories just by using this perturbation theory. And also in the in-spiral, yeah, approximations can be used to go there, post-Newtonian to, I don't know, third, fourth order are being used here.
All right, thank you.
Okay, thank you very much. I think we should move on to our next speaker,